Hello everyone, welcome to Design and Analysis of Algorithms. In this lecture, we are learning about minimum spanning tree, and already in the last two parts, we first saw the definition of minimum spanning tree and one meta algorithm, and we saw Kruskal and Borufka in the last second part. In this part, we'll talk about Jarnik-Prim algorithm. So let us recap very quickly. In minimum spanning tree problem, we are given a connected, undirected, weighted graph. The graph has vertex set V, edge set E, and a weight function W, where it can be positive, negative, or zero, the edge costs. Our goal is to return a spanning tree. Spanning means it should connect all the vertices, and tree, it should be a cyclic subgraph. And in this tree, we want to minimize its cost, which is the sum of all the the cost of all the edges which are present in the tree. So this is the cost of the tree. And then we saw three types of edges: useless, safe, and undecided. And safe edges are those edges, if we take any component, so we maintain a subgraph, a cyclic subgraph. In the beginning, we have n one vertex graphs, and then we grow them, and at the end, we get the entire graph. And we add some edges iteration by iteration, and we call an edge is safe if for a component f, it is the minimum weight edge that is leaving the component. That means that it has one endpoint in this component, and other endpoint is not part of the component. And then we proved that MST will contain all the safe edges. And we saw this meta algorithm where we tried to add safe edges. And we already saw two variants. In one, Kruskal, in other one was Borufka's algorithm. We saw how to create MSTs by adding safe edges in different ways. In one case, we sorted the edges and then we added. And in the other case, we look at the components and we add all component edges at once. So this was Borufka. And now we'll learn about Jarnik-Prim's algorithm, which is also known as Jarnik's algorithm, Prim's algorithm. There are several names, and we'll talk about the history in the last part. But in this part, we'll only focus on Jarnik-Prim's algorithm, why it works and how it works. So remember, the definition of safe edge is again here. An edge is safe if for some component of f, it is the minimum weight edge leaving f. Now, if we look at Jarnik's algorithm, what the algorithm is, one line algorithm is we repeatedly add T's safe edge to T. We start with one vertex and we repeatedly add the safe edges. Think of the algorithm quickly. What is happening is, given this graph, we start with a root vertex. And in this case, we can take any root vertex. Finally, the output will be same, but for now, I assume we have taken this as a root vertex. Then for this single vertex, it's a component. There are three edges which are leaving. We'll take the edge which is cheapest, which is leaving, that is 4. So we take this edge here to be part of the component, to be part of T. Now T is this. And now we again look at all the edges which are leaving T, 18, 12, 24, 14, and 26. And we find 12 is the cheapest edge among them. So we add 12. So now T is becoming this. Then among this component, all the edges which are leaving the component 18 to this, we are finding 2 is the minimum one. Now we are no more considering this edge because this is an useless edge. Both the endpoints are in the same component T. Then we add 2. Then this becomes T. And then the next we find 8, 10, 3, 30, 26, they are leaving. And out of them, 3 is the cheaper. So we'll add 3 here. So this graph becomes this. And then again, among all the edges which are leaving this component, we find 8, 5, 16, and 26, and 30. Cheapest one is 5. So we add 5. And finally, we find 16 is the edge which is cheapest among the edges which are leaving here. So we add 16, and this becomes the final tree. Everything is connected. And we can verify the same graph we have used for Kruskal and Borufka, and we got the same output. Even in this case, we could have started with some other vertex. Instead of this vertex, we can start with this vertex or this vertex. You can try, and we'll reach the same tree again. This is Jarnik-Prim's algorithm. Now we'll focus on the details of the implementation. And for that, let me take a detour and go to what is heaps. Now, I will not go in details about the implementation of heap. I'll just basically describe the operations, not the detail, and the runtime required for the operation so that we can know this information and use in the algorithm. The details are there in the books. You can read about them, and maybe I can also post videos later about the details of implementation of heaps. Now, heaps can be of two types. One is mean heaps, other one is max heap. In this example for Prim's algorithm, or previously, or maybe we'll also see Dijkstra's algorithm sometime, we'll use something called mean heap, where it looks like this. Either we can have a binary tree representation or an array representation. So this one is a mean heap which satisfies, it's a binary tree, and it has a property that for each object x, let's say this is object 3, its children are 5 and 9. So both x dot child children, if I take any children and the node itself, the value of the children, we call it key. Key should be more than the key of the parent. So always the key of parent is less than equal to the key of child. That is mean heap property. In max heap, it's opposite. Always the key of parent is greater than equal to the key of its child. We can verify. And again, max heap can also be represented by arrays. So you can check why this is a mean heap, this is a max heap. And the properties of heaps, there are nice properties. So there are some operations that we want to maintain. So one is insert, that given a heap, we want to add a new object and we want to add the object. So for example, in this heap, let's say I give you a key of 7. I want to add it. That's the insert operation. And it turns out it takes, for if there are n objects, it takes order log n time to do an insert in a heap. And if it's a Fibonacci heap, I'll not talk about the details. You can even do better. You can do an amortized constant time. Then there's another operation called extract mean. Given the heap, I want to find the minimum element and I remove it. By minimum, I mean the element with the minimum key. In this case, like 1 is the minimum key. Similarly, for max heap, we can do extract max. We can find the maximum element 16 and remove it. And after that, we still want to maintain the property of the heap. We want to create another heap which contain all the elements except the removed element. So it will require some more modifications, and it turns out even that can be done in order log n time. So insert and extract mean are two useful properties in heap, and this can be done very fast, this extract mean in log n time. Other operations are find mean for mean heap or find max for max heap, where we just want to find the object with the smallest value, smallest key. We are not removing it. Heapify, when we create the heaps, we give the initial n objects in order n time. You can create the heap. Delete, you can delete an object from each. You give a value and we find that object and delete. It can again take order log n time. And then there is another very important operation called decrease key. We give an element x, and maybe x has value 16 right now. I want to decrease it to 12. Even that can be done in decrease key in mean heap, or in case of max heap, it will be increase key. And in binomial heap, which in the figure we are showing binomial heap only, it takes order log n time. But if you use Fibonacci heap, you can do even better. It's constant time amortized. So what I mean is, let's say here, I want to reduce this 16 to 15, let's say, or 12. So I change the value and then there will be some modification in the tree, but that can be done quite quickly. That can be done only in constant time amortized way, or in binomial heap, it will be order log n time. In general, heaps are very useful object when you have some you need to compute the very fast minimum or maximum of among some elements, and these elements are dynamically changing. And we'll see exactly this application in case of Jarnik-Prim. So this was a very very quick recap of heap. It will take some time to go over the details. If you are interested, read CLRS or any other books which talks about details. But for now, what we need is from this is, given a heap, if we have n number of elements, we can heapify. We can create the heap in order n time. We can do extract mean in order log n time. We can insert an object or decrease key, these operations in mean heap, in Fibonacci heap, in constant amortized time. Now with this, we are ready for Jarnik-Prim's implementation. So now let's see in more detail how Jarnik-Prim is implemented. This is the algorithm. So we are given G, the graph, W is the weight function, And we start with the root vertex, which is R. In this case, let's say we start with E. This vertex to be the root vertex. Maybe we have A, B, C, D, E, F, G. There are 7 vertices in this example graph, and this is the root vertex. Now we'll define key and parent, two attributes for each vertex. Key will contain a value which will basically contain the minimum weight of any edge connecting that vertex to some node in the tree. And that node which is connecting this node with the tree is called parent node. So for example, we'll see some example, but let's say we have some vertex D here, and maybe this is the cheapest edge which is connecting D with E. Then E is the parent, and the value of the key of D will be 26. We'll see more details how it works. Now for the root node, we make sure the key is 0, and we also define a queue, which is all set of all vertices. So then we create a heapify, which I mentioned for n elements it will take, or v elements it will take order v times, or order n times for n elements. Now this is a loop, and then we return tree as vertex and their parents at the end for all vertices except root. And we'll see how it runs. But now let's focus on the loop. First, what we do is we do extract mean in the queue. Now remember, in the beginning, every node has value infinity. Only the root node R has key 0. By value, I mean key. This is interchangeably used here. Now, when we extract the vertex U, for each vertices which are neighbors of U, we do an update. We see whether we can reach this new vertex V through U in a cheaper edge. If it happens, we update the parent of V to be U, and we update the key of V to be the edge cost between U and V. Now let's look what is happening in this graph. As I mentioned in the beginning, everything is infinity. All the keys are infinity except E, which is the root vertex for which it's 0. So all these green vertices and the orange vertex, the colors are showing that they are part of Q. And orange is showing that it is the minimum value in the queue right now. If we do extract mean, I will get E here. This is the first step. Then for all neighbors of U, in this case, E has 3 neighbors, F, G, and D. We do this operation. Like if V is part of Q, right now all are part of Q. And then we look at the edge cost. If it is less than the key of V, right now all this has key value infinity. And as the edge between U, E, F is less than the key of F, we'll update the key of F to be W of EF. That's what we're doing. So for this edge, we see the edge cost is 4 and this is infinity. So we update this to be 4. And then similarly, for this edge is 14, we update 14. And then for this edge is 26, we update 26. Previously all were infinity, so we are updating. And we write E to be the parent for all of them. So red is showing the parent, E, E, E for all 3. Now after doing this gray color is showing that this vertex is removed. E is removed now. The remaining vertices are there in the queue. So now we again do extract mean. And now everything is infinity here, except this is 4, this is 14, this is 26. Among them, 4 is the minimum. So now this becomes the extract mean vertex. And now I look at all its neighbors. Now this has value 18, this has value 12. So earlier it was infinity, so it's updated to 18 and the parent becomes F. Now this edge, earlier the value was 14 and the parent was E, but now this is a cheaper edge, 12. So we'll update it to be 12 and parent to be F. Intuitively, what is happening is we are looking at this whole component, and already we have computed the values for the edges which are connecting to this component. And now we're also looking at the new vertex and looking at if there are other ways to connect to this component through this vertex. And if there are cheaper edges, we are just updating and we are just iterating over each edge. So we are actually adding the safe edges in this way. Though explicitly we are not mentioning what are the safe edges, but at the end we'll see that if I have some node at the end, that node and its parent, they are safe edges. Okay, so now we have this object. And then again, we go for the extract mean, and this has value 18, 12, 26. This is the minimum one. Other two are infinity. So this say I take F, not F, this is vertex G. And then we look at its neighbors. And we do the same. This has now value 2. So from 18, it is updated to 2. and G, this vertex becomes parent of this vertex. So G becomes parent. Similarly, this is 3, so it becomes parent G. And this is 30, so previous value 26 is still there. So we get this new case. And now this F, E, and D, these 3 vertex are not part of Q anymore. We continue. Now among all these 4, minimum value is 2. So we take this vertex and try to update its neighbors. And we see this is 5. So note that we're not adding useless edges. This is, for example, useless edge because already this is part of, this is not part of the queue. E is not part of Q, so we are not adding the useless edges. So similarly here, when we have 2, we add the edge here. We look at the edge cost of 5 and we update. And then we go to 3, we see, okay, this is actually edge cost 5. It's even cheaper compared to the previous case. So we update this to be 5 and C. And finally, we look at this vertex, this edge, and we find, okay, this is even 16 cost. Earlier it was 19 and C. This is even cheaper. So it becomes 16 and C. Okay, wait, it's 19 and C. There is some mistake. It should be 16 and C. And this way we continue, and at the end, we got this graph. And you can start with any other vertex instead of E. We could have gotten the same. The process is simple. We start with everything, every key is to be infinity, parents are null, and we start with the root vertex, that's the extract mean. And then we look at all its neighbors, which are not, and if they're part of Q, we update their keys if the edge is small, the connecting edge is small, and then we update that to be parent. Now, after doing all this, we return the MST as this thing. And if you look at the parents, in this graph, we'll see parent of A is C. So we add an edge between A and C. Then we see the parent of C is G. So we add an edge between C and G. And we continue. This is just following the same way we have grown the graph. And at the end, this is just keeping track of how a vertex was added into the tree, and we're just adding them back. And this will give you the MST. So pause the video for maybe 5 minutes and go over this in detail. You'll realize that this is exactly the graph that we'll get from the algorithm. Now, about the runtime, we see there are V extract mean operations which are being done, and Heapify will take order V time, and there are order E number of decrease keys happening. So this operation, extract mean, we are doing again V number of times. Each vertex is extracted only once. And for each edge, we are checking this fact. So this decrease key can be done order E times. Now, as I mentioned, for binomial heap, this will take log E log V time. This will also take V log V time. So overall, it will take V plus E log V. Whereas in Fibonacci heap, you can do it much faster. Decrease key operation, you can do in constant time. So you can get only order V plus order V log V plus order E, which is roughly order E plus V log V. Okay. So this ends the algorithm for Jarnik-Prim. And the next part, we'll talk about these algorithms, the history of these algorithms, comparison, which one is better when, more about greedy algorithms and more extensions and more applications of spanning tree. Thank you.